What if everything you see, hear and feel is just a projection? What if the world around you, the very fabric of your existence, is nothing more than an elaborate illusion crafted by your mind? Imagine a world where our senses deceive us, where the bustling cityscape and the busy streets are mere figments of our imagination. Our eyes, ears and hands, the very tools we rely on to interpret reality, could be leading us astray. Picture a scenario where the solid ground beneath our feet is but a shimmering mirage, a trick of the light that vanishes upon closer inspection. This is the world we might be living in, a world where nothing is as it seems. This is not the plot of a science fiction movie, but a serious scientific theory known as the Holographic Universe Hypothesis. This hypothesis suggests that our entire universe could be a sophisticated hologram, a projection of information encoded on a distant two-dimensional surface. It suggests that our three-dimensional reality might be a holographic projection of information encoded on a distant two-dimensional surface. This means that everything we perceive as real, from the smallest atom to the vast expanse of the cosmos, could be an illusion. This mind-bending idea challenges our very perception of reality, and forces us to question the nature of existence itself. It compels us to rethink everything we know about the universe and our place within it. The concept might seem absurd at first. After all, we experience a three-dimensional world filled with depth and texture. We laugh, we learn, we question, all within this seemingly solid reality. We experience a three-dimensional world filled with depth and texture. Our hands can touch and feel the roughness of a surface. Our eyes can see the towering buildings that surround us. How could this be a mere projection? How could this be a mere projection? The answer, physicists believe, might lie in the strange world of quantum mechanics and the enigmatic nature of black holes. These phenomena could hold the key to understanding the true nature of our reality. The answer, physicists believe, might lie in the strange world of quantum mechanics and the enigmatic nature of black holes. These cosmic entities with their mind-boggling properties could provide the clues we need to unravel this mystery. The journey to unraveling this cosmic mystery began with attempts to understand the universe's most extreme objects, black holes. These swirling vortices of stars and gas, with their immense gravitational pull, have fascinated scientists for decades. These cosmic monsters, formed from the death throes of massive stars, possess gravitational pull so strong that nothing, not even light, can escape their grasp. They are the ultimate enigma, challenging our understanding of space, time, and reality itself. As we delve deeper into the heart of this theory, we'll explore the groundbreaking work of physicists like Stephen Hawking and Juan Maldacena. Their pioneering research has paved the way for new insights into the nature of our universe. We'll journey to the very edge of reality, where the line between science fiction and scientific fact blurs. We'll explore the frontiers of human knowledge and imagination, seeking answers to the most profound questions about our existence. Fasten your seatbelts, for we are about to embark on a mind-bending adventure into the depths of the holographic universe. Prepare to have your perceptions challenged and your understanding of reality transformed. The Holographic Universe Hypothesis, born from the marriage of quantum mechanics and the profound insights of theoretical physics, has captivated the minds of scientists and enthusiasts alike. This hypothesis suggests a radical rethinking of our understanding of the cosmos. Rooted in Einstein's theory of general relativity, it proposes that our universe is akin to a giant hologram. Einstein's groundbreaking work laid the foundation for this idea, intertwining the fabric of space and time in ways that continue to challenge our perceptions. In a hologram, a three-dimensional image is encoded on a two-dimensional surface like a credit card. This concept is not just a metaphor, but a literal description of how information might be stored in our universe. Similarly, this theory suggests that all the information about our three-dimensional universe could be encoded on a distant two-dimensional surface, like a cosmic movie screen surrounding us. Imagine the vast expanse of the cosmos, with every star, planet, and galaxy being a part of this grand projection. But what does it mean for the universe to be a hologram? This question delves into the very nature of reality itself, challenging our most fundamental assumptions about existence. It suggests that our perception of three dimensions, height, width, and depth, might be an illusion, a sort of cosmic trickery. Just as optical illusions can deceive our senses, the universe might be playing a grand illusion on a cosmic scale. Just as a hologram appears to have depth and texture despite being a projection from a flat surface, so too could our universe be a projection from a lower dimensional reality. This idea opens up new avenues of thought and exploration, pushing the boundaries of what we consider possible. This revolutionary idea has its roots in the study of black holes. Black holes, with their immense gravitational pull, have long been a subject of fascination and mystery. Stephen Hawking's groundbreaking work revealed that black holes aren't entirely black after all. His theories have reshaped our understanding of these enigmatic objects. They emit a faint radiation, now known as Hawking radiation, which slowly causes them to evaporate over vast cosmic timescales. This discovery was a monumental step in bridging the gap between quantum mechanics and general relativity. This discovery led to a profound puzzle. If black holes evaporate, what happens to the information they consume? This question has sparked intense debate and research within the scientific community. Quantum mechanics dictates that information cannot be destroyed, yet it seemed to vanish into the abyss of a black hole. This apparent contradiction has profound implications for our understanding of the universe. This paradox, known as the black hole information paradox, hinted at a deep connection between gravity, quantum mechanics, and the nature of information itself. It suggests that the answers to these mysteries might lie in the very fabric of reality, waiting to be uncovered by the curious minds of future generations. To grasp the essence of the holographic universe, imagine a closed box containing a variety of objects. Each object inside the box has its own unique properties, such as size, shape, and position. Traditionally, we would describe the system by detailing these properties individually. The traditional way to describe this system is by specifying the properties of each object, its size, shape, and position. This method is akin to how we perceive the universe around us. This is analogous to how we perceive the universe, a vast collection of stars, planets, and galaxies, each with its own set of characteristics. We observe and measure these celestial bodies to understand the cosmos. However, the holographic principle offers a radical alternative. Instead of focusing on the individual properties of each object, it suggests a different approach. It suggests that instead of describing the contents of the box, we could instead focus on the information encoded on its surface. This surface information could potentially describe everything inside the box. This information would describe the interactions between the objects inside the box and their effect on the box's boundary. Essentially, the surface holds the key to understanding the entire system. Think of a water balloon. You can describe it by its volume, the amount of water inside, or you can describe it by its surface area, which stretches as you fill it. The more water you add, the more the surface expands. Surprisingly, these two seemingly disparate measures are directly linked. The volume and the surface area are interconnected in a fundamental way. The relationship between volume and surface area in a water balloon is a simple analogy for the holographic principle. It suggests that the information content of a region of space is not determined by its volume, but by the area of its boundary. The holographic principle suggests something similar might be true for our universe. This means that a vast three-dimensional region of space could, in principle, be described by a set of information encoded on its two-dimensional boundary. This principle, while seemingly counterintuitive, has profound implications. It challenges our conventional understanding of space and information. It suggests that the information content of a region of space is not determined by its volume, but by the area of its boundary. This idea could revolutionize our understanding of the universe. This means that a vast three-dimensional region of space could, in principle, be described by a set of information encoded on its two-dimensional boundary. This concept is not just theoretical, but has practical implications in fields like quantum physics and cosmology. This mind-bending idea forms the crux of the holographic universe hypothesis. It opens up new avenues for exploring the nature of reality and the fundamental structure of our universe. Black holes, once considered cosmic oddities, have become central to our understanding of the universe, particularly in the context of the holographic principle. Their immense gravity warps the fabric of space-time, creating a region where the laws of physics as we know them break down. Stephen Hawking's discovery of Hawking radiation was a pivotal moment. He showed that black holes are not eternal prisons. They slowly leak energy and eventually evaporate. However, this discovery raised a perplexing question. What happens to the information that falls into a black hole? The answer, according to the holographic principle, is that the information is not lost but encoded on the black hole's event horizon, the point of no return beyond which even light cannot escape. This suggests that the information about everything that falls into a black hole is preserved, not within the black hole itself, but on its two-dimensional surface. This insight has profound implications for our understanding of the universe as a whole. If information can be encoded on a lower dimensional surface in the case of black holes, could the same be true for the entire universe? This question lies at the heart of the holographic universe hypothesis. String theory, a leading candidate for a unified theory of physics, lends further credence to the holographic principle. Unlike traditional physics, which views fundamental particles as point-like objects, string theory proposes that everything in the universe is made up of tiny vibrating strings of energy. Just as different vibrations of a violin string produce different musical notes, different vibrations of these fundamental strings give rise to different particles and forces. String theory operates in a universe with more than the three spatial dimensions we perceive. These extra dimensions, curled up and hidden from our view, play a crucial role in the holographic nature of reality. It's within this framework that physicist Juan Maldacena made a groundbreaking discovery. Maldacena found a mathematical connection between string theory in a five-dimensional spacetime and a quantum field theory existing on its four-dimensional boundary. This duality, known as the ADS-CFT correspondence, provided the first concrete example of the holographic principle in action, demonstrating how a gravitational theory in a higher dimensional space could be equivalent to a non-gravitational theory on its lower dimensional boundary.